Okay, so we are continuing our discussion on confidence intervals for a mean, and we're actually finishing off our chapter with this video. As a review, there are three conditions you have to check before you can do a confidence interval problem for a mean. I'm going to write them down, but see if you can remember them yourself. So pause me if you want to write them down yourself. We have our random sample condition. Data needs to come from an SRS. We have our 10% condition. And then we have one of two things that we can do for that third condition. We can either establish that the population is normal, or if we don't know the population is normal, if our sample size is at least 30, we're still good to go. That result was called the central limit theorem. So, in review of why we check each of these conditions, remember that we do a random sample to make sure that we don't have sampling bias in our data. The 10% condition ensures that our picks are approximately independent when we sample without replacement. That allows us to calculate our standard deviation. And then this last condition right here is what makes sure the t distribution that we end up using is actually okay to use. Now, it turns out that the t distribution is what is called in statistics, kind of an interesting concept. It's called robust. So you would say that the t distribution is robust. And what that actually means is the t distribution does a pretty good job of working, even when conditions aren't especially ideal. So in the event you're using a t distribution, you can actually still get by if neither of these two things is met. In other words, you don't know your population is normal and your sample is smaller than 30. What you can do instead is look at a graph of the sample data. So what you're going to do is you're going to look at a graph of your sample data. If there are no outliers or strong skew, you can still use the t distribution. So basically, what's going to end up happening, there's one more kind of wrinkle in the process right here that we have to talk about. Let's say you strike out on, oh gosh, my population isn't normal. Oh, my sample is not at least 30. It turns out the t distribution can still get the job done as long as your sample isn't dreadfully skewed or doesn't have outliers in it. The reason that we check this, when we say there are no outliers or strong skew, what that does for us is it says it's at least plausible that the population is normal. And it's the population that this tests to be being normal, not the sample. So what is even going on? What does that mean? Well, let's say I take a little sample out of a data set and I get this for my sample. Okay, so this data set right here doesn't have super strong skew. It doesn't have any outliers that are way beyond the scope of the other points. So we'd be like, I guess that could have come from a normal distribution population because it doesn't look super skewed. So we'd be like, okay, yeah, t distribution, you can still work on a problem like this. Whereas if I had a data set that was just severely skewed, maybe there is even an outlier or two on top of that, this probably did not come from a normal population, so a t distribution wouldn't work very great on that. But if your data set is sort of symmetric and so on, the t distribution still does a good job getting us our estimates. Okay, so that is a third thing to remember with that extra condition. So there's going to be a 4-step process. We actually practiced it in the last set of slides at that last example. And you can use your calculator for one of the commands, or use the calculator command rather than the formula, just like I taught you with P problems. So let me show you where that button is on your calculator. We're going to go stat and tests, just like we did before. This is going to be our new favorite menu here. We already learned choice A, 1 proportion z interval. There's going to be another command, number 8, that is called a t interval. So as of now, we know A and we know 8. stats. Those are our two for this chapter. So we're going to go on our calculator to stats, and then to tests, and then to number 8, which is called T interval. And this is like going to be our shortcut for when you do a 4-step problem, just like we had a shortcut last time. So let's talk about how this actually works and do an example. So these girls are going to be doing their AP statistics project, and they're looking at how well different just one brand, I guess, how well does this brand of generic toilet paper absorb water? So they take a little cup, and then they figure out how many sheets it takes to absorb all of the water. And these are going to be their results from each of 18 different randomly selected roles. So let's go ahead and set up a 4-step process. We want to construct and interpret an interval for mu, which is the true mean number of squares it takes to absorb the water. So based on our data, those 18 points right there, what we want to do is figure out on average how many squares does it take to absorb the 4th cup of water. So first thing you do is write down your state step. So we're defining our variable. I realize that they did it right here, but it's still a good habit to write out. So we want to estimate with a 99% CI, mu equals true mean number squares of TP to absorb 1/4 cup water. Then it's time to check our conditions. So when we check our conditions, first of all, it's a random sample of 18 rows. That's good. 18 is totally less, 18 is less than 10% of all generic TP roles. And then we have our third condition. It doesn't say, oh, the population of number of squares is approximately normal. It doesn't do that for us. It also is only 18 rows. It's not enough to hit that 30 threshold. So what we need to do instead is graph our data. And we're going to do that on our calculator here. So I will remind you guys of how that works. We're going to go stats, edit, and then we're going to punch our 18 numbers into the calculator. I'll go ahead and throw those in there. All right, so I typed those in the calculator. And then once you do that, you're going to go second quit, go to second y equals, stat plots. I'm going to turn it on. And honestly, you can do this a couple ways. The histogram would be all right if you wanted to look at shape that way. But the box and whisker plot with the outliers, this guy right here is actually the best option, or the easiest option in my opinion, because it'll show you outliers and you can look at skew, and those are the two things you care about. So I'm going to choose that. And then I'm going to zoom stats, number 9, and it's going to show me my nice looking box and whisker plot. So if I look at this graph, perhaps it is very slightly skewed to the left. This side looks a little bit more stretched out than the other side, but it's not bad. This data set is fairly symmetric right here. There are no outliers or dots present. So what that tells us is, yeah, the population could be normal. So we graph the sample data to see, could the population perhaps be normal? If we were seeing dots for outliers and just strong skew, then we couldn't make that assumption and it wouldn't work out for us. So we need to sketch this little box and whisker here. If you hit trace, you can get your 5-number summary. So I got 20, 23, 25, 27, 29. Let me see if I can remember that. And then what you're going to do is look at your calculator screen. It doesn't have to be a fancy looking box and whisker plot. Let's see, I think going by memory here, that side was a little bit longer. But truly, they don't want you to waste a bunch of time making a crazy graph here. We got 20, 23, 25, 27, 29. I'm pretty sure that's what the number said. If I'm wrong, just fix it. So what we would do with this is we would say that there are no outliers or strong skew You could also say, oh, the data appears symmetric, but then you're making a stronger statement. So you're saying, oh, it's totally symmetric. Even if it's a little bit skewed, we're all right. So I'm just going to say it's not strongly skewed as opposed to symmetric. So that tells us that the t distribution is appropriate. So that's like an annoying little extra step. Oh, I got to graph my sample data, but it's not bad. You just throw the little box and whisker on your screen. You say, hey, it's not strongly skewed, no outliers. So we're going to keep on moving with our t distribution. So the good news is, now that we have our data in the calculator, it's actually already in there when you go to do the tests. So we're going to go stats, and then we're going to choose tests. For a mu problem, you will choose t interval. T interval is our setup right here. And there are actually going to be two tabs. The first option is if you have raw data. The second option is if you're doing where they just tell you, oh yeah, my sample mean is this and my standard deviation is this. So they gave us a list of 18 numbers. We want the data tab. But if they didn't give us that list and they were like, oh, they found the average was 21.7, you would type it in right there. We want data. And I already typed it in L1 earlier, so it's there already. I don't have to go do that now. If I hadn't graphed my data, I would. Then my data is in L1. They want a 99% confidence interval. And then we're going to hit calculate. So it's going to spit out the interval right here. The things that you need to report when you use the calculator, you need to make sure you name the test. The test is called, or the interval style is called a t interval. You need to give the actual interval. So 22.99, 26.90, 22.99, 22.99 to 26.90. Is that what I said? Yeah, 26.90. You do not have to include the X bar and the S. You can if you want to, but you do need to report the degrees of freedom. If you forget that, it will take off on the AP test, and the calculator doesn't say it, so you have to kind of remember, oh, degrees of freedom. They tell you the sample size is 18, so you need to remember that the degrees of freedom for this problem is going to be 17. I'm actually going to go back to the last slide, and I want you guys to add this in. Make sure where you're writing down what's going on here, put a star for yourself on this side, and put down like remember DF. That's not going to work right there. Just write down on this slide right here to remember to write down the degrees of freedom. So we've got that. And then you guys can go ahead and write a conclusion. I will pause and throw it up there. All right, so I've got my conclusion written in orange up at the top there. We're 99% confident that the interval from 22.99 to 26.90 captures the true mean, make sure you mentioned average, number of squares of TP required to absorb a fourth cup of water. So it's actually, if you take a step back, kind of cool when you do this, in my opinion. These girls only took one sample right there, and they got an average for their sample. But if they use statistics, they can get a lot more confidence about the overall average and just get more quality information than just reporting a single average by itself. You get a whole range of values right here. So it's kind of neat. All right, these problems right here where it says like construct and interpret, you can recognize these sorts of problems in general because they give you like a bunch of blank space. Anytime they say to do this, even if it doesn't say on the problem, do the 4-step. When you're expected to do these long problems where you make your interval and interpret it, just always do that 4-step process. Very last thing in the chapter we have to talk about is how you figure your sample size to get a certain margin of error. We did this last section in 8.2 with P problems. Now we're going to do it with mu problems. So if you recall, what you're supposed to do is take the thing after the plus or minus sign. So our little setup for a confidence interval goes like this. And you take your margin of error, the guy after the plus or minus sign, and you set it less than or equal to whatever you want your margin of error to be. That's what we did in the P lesson. But if you look at this setup right here, I have a T star critical value. So if I go to do an inverse T, because I would have to find T star for this setup here, inverse T. It's going to ask me for my area. That's fine. I can figure that out. It's also going to ask me for my degrees of freedom. Degrees of freedom is n minus 1. Sample size minus 1. But when you do this kind of problem, you are trying to find your sample size to give you a certain margin of error. So you're in this loop that you can't break. I need T star to get n, but I can't get T star unless I already have n, because degrees of freedom is based on your sample size. So this little setup here actually doesn't work for us because we can't get T star. So the way that we fix this right here, it's a little bit of a workaround. But what we end up doing, in my tomato thing last lesson, we talked about how Z star would be cool if you actually knew sigma. So we have this setup going on way down here at the bottom. It's basically the first method from the last video that we talked about. We're usually not going to know real sigma, not realistic. But we can't do it this way because we don't know degrees of freedom. So we just act like, okay, yeah, I'm just going to say I know what sigma is or guess what I think it is. And then I'm going to use a Z star, which doesn't make me know n ahead of time. Okay? Hopefully that justification makes a little bit of sense. Is it going to be 100% precise? No. But at the same time, it's still good information. All we're trying to accomplish when we do this sort of problem is figure out about how many data points do I need to get the margin of error I want. So you're just ballparking things anyway. So you guess a sigma, and then you go from there. This message is from my calculator, which keeps crashing. Sorry, that keeps popping up. So let's finish with one example problem. They are trying to figure out the amount of time on average that students spend on homework during a typical week. They are going to do a 90% confidence interval for that average mu. And they're comfortable with a margin of error. Now, in P problems, we'd say like, oh, 4%, 5%, or whatever. But mu is usually measured in the units of the problem, which in this case is minutes of study time. They don't want to be off by more than 30 minutes. So what we're going to do, again, normally it would go like this. We would take that less than or equal to 30. But you can't do it this way because we don't know T. So what we do is we do a Z star, and then we act like we actually know sigma, or maybe we have like prior results that tell us what we think sigma is. So they did a pilot study here, and they think the standard deviation is about 154. So what I would do is I would do a 154 for sigma, and then I would need to find my Z star. So I would do an inverse normal for a 90% confidence interval. Like I said, this is one of two that I actually know. So you would do an inverse normal, not an inverse T, and get this setup right here. After you do that, you're just doing regular easy algebra to get n all by itself. So let me see if I can do this without screwing it up here. I got 71.3. So I divided by the 1.645. I multiplied by root n. I divided by that number. And I got 71.31 with n over here. And then remember, you will never give me a decimal for this. These are people here. Always bump it up to the next whole number. They need at least 72 students to get a margin of error of no more than 30 minutes. So that is the end of chapter 8.